today we are going to talk about the physical instantiation of information in black hole and how it gets out of black holes. There are a couple of mysteries about black holes. When a black hole gets created, what happens to the information in all the matter that has collapsed into the black hole? If it is a collapsing star, before the star becomes a black hole, the information is instantiated in the matter that makes up the star. Every electron instantiates the information about its own spin, for instance. Once the black hole collapses, all the matter, according to classical GR, collapses into the singularity in the center. So what happens to all this information? Now, we also know that the black hole radiates, so black hole evaporate. And when the black hole has evaporated, what happened to all the information that was inside? Presumably, it has been imparted to the radiation that is coming out. When Hawking first discovered that black holes radiate, part of the discovery was that the radiation is purely thermal. It has no information content whatsoever. And indeed, how could the information come out if nothing can come out of a black hole? This is something else that we will address. We're also going to see why the radiation is inversely proportional to the mass of the black hole. This is one of the discoveries of both Bekenstein and Hawking. Bekenstein simply showed us that the temperature of the black hole radiation is inversely proportional to the mass. Hawking later on provided the precise proportionality constant. We're not going to get to the proportionality constant, but we will show that the colder black holes have lower temperature, that the bigger black holes have lower temperature. There's another question that has to do with charged black holes. What happened to the charge of a black hole if it has some electrical charge as it evaporates? Often you could imagine that the black hole has some sort of a charge, which just so happens that the matter that collapsed was not exactly neutral. As the black hole evaporates, the charge becomes condensed into a smaller and smaller volume. What happens to it? We are going to see that we don't have to worry about. A charged black hole is very efficient at getting rid of its electric charge way before it starts to become a little black hole. Even a giant black hole is very good at getting rid of its electric charge. And the smaller it is, the more efficient it is at getting rid of its electric charge. We are also going to consider some implications of momentum conservation, and we will see that this is going to lead us to some quantum statistical fluctuations inside the black hole that at this point, I have to admit, I don't quite understand their meaning or their significance, if any. But we are going to see why we have those fluctuations. And finally, we will discuss the stress energy tensor inside the black hole, which leads to some more open questions for which at this point I don't have any answer, but it is good to be aware of any such issues. So let's start with why is the information in the black hole? And most theories that deal with black hole information claim that the information is not inside the black hole, because if it is inside, it can never escape. The claim is that the information is outside the black hole. And one argument as to why it should be outside the black hole. And by the way, let me state very strongly up front that I'm going to mention my understanding of contributions from several physicists, and the way I represent their contributions should not be taken as being accurate in any way whatsoever. I may misunderstand what they say. I may simply have forgotten exactly what they said or misrepresent what they say. But at the same time, I want to make sure that I give credit where credit is due. One reason why we can expect information to be on the surface, right outside the surface of a black hole, the surface, I mean, the event horizon, is given by Lenny Susskind, and the argument is as follows. If I drop a pen into a black hole, I'm going to see the pen collapsing into the event horizon of the black hole. I would see it moving ever more slowly towards the event horizon, becoming ever more shifted, but never crossing the event horizon. So as far as I'm concerned, as an outside observer throwing pens into a black hole, all the information embedded in the pens that I'm throwing is conserved or is embedded just outside the black hole. This is in the top left quadrant of this set of cartoons. Can you guys see my, so hopefully we are in business. So in this picture right here, I throw a pen into the black hole, and the information, as far as I'm concerned, looking at the pen, I see it stuck at the surface of the black hole. So I conclude, yes, all the information is right outside the black hole. Now, suppose that there's somebody else standing on the other side of the black hole. After I threw my pen into the black hole, this guy is throwing an Earth-sized planet into the black hole. As soon as the black hole has absorbed this Earth-sized planet, its radius is going to increase by 1 centimeter. 1 centimeter is about the Schwarzschild radius of planet Earth, roughly.
1.2 miles, taking a left.
So what I'm going to see when this happens, I'm still going to see the pen exactly where I saw it the last time, except that it will be further redshifted and it will be dimmer. By observing the redshift, I should be able to figure out exactly what happened. At least I should be able to figure out that something weighing as much as planet Earth has been thrown into the black hole. Now, after this has happened, I'm going to throw another pen into the black hole. I'm going to see that the other pen is going to reach a point 1 centimeter away from the first one. It will never reach the first one because now the event horizon has shifted by 1 centimeter. So I'm not going to see the information embedded in this pen and the information embedded in that pen in one single membrane. I will see them 1 centimeter away from each other. So what I'm going to see in this case is that the information is not on the surface of the black hole. I'm going to see information inside the black hole.
0.1 mile.
So if I take Susskind arguments seriously, and I take it to its ultimate conclusion, the conclusion is that the information is not on the surface of the black hole, but inside the black hole.
Northwest for 1.5 miles.
This argument can be made even stronger by looking at this last picture,
You're going to take a
where
left
I
on
have
the main.
a shell of dust that is going to collapse into a black hole. The solid black line represents the event horizon corresponding to the mass of the shell of dust. To begin with, the shell of dust is way outside its corresponding event horizon. Now, inside the potential event horizon, I have a mouse. Looking at the mouse from far away, I see it doing its own business. As the shell collapses, I'm going to see the mouse still exactly where it is. It's not going anywhere, but I'm going to see it ever more redshifted. When the shell of dust reaches its black hole limit, its Schwarzschild radius, I'm just going to notice that the mouse is even more redshifted, and I'm not going to get any further information above and beyond what the mouse did later on. Any questions so far?
Yeah, I have a question.
Go ahead.
If the information, as you say, is within the event horizon now, how does it ever escape?
Excellent question. Excellent question.
Second part two, is, and I'm very unclear on what the theory is here on Hawking radiation. Hawking radiation, is this thermal radiation or is this entropic radiation?
According to Hawking's initial calculations from the 1970s, the radiation is purely thermal. It does not contain any information whatsoever.
Then it violates unitarity.
Exactly.
Well, how do we justify that in it being consistent with quantum mechanics?
One moment. Yeah, there is a violation of unitarity. This is the information paradox. And since then, people have tried very hard to show that the radiation is not thermal, but it contains information. It contains all the information that was initially in the black hole. And we're going to talk about this. The action is we're going to start very safely from way far away, where the gravitational attraction of the black hole is negligible. Far away, we are in a flat Minkowski space, and quantum field theory tells us that we have all the time creation and annihilation of, let's say, electron-positron pairs, as well as quark antiquarks and everything else. And because of conservation of energy, we violate energy when we create such a pair. This pair can exist only for a very short amount of time. Gravitational potential is negative because it is attractive. So if we have a particle at rest closer to the black hole, and we're going to see this in more detail in a minute, it has negative energy, it has less energy if it is instantaneously at rest. So an electron instantaneously at rest here is going to have less energy than an electron instantaneously at rest further away. Therefore, the pair that we create here is going to have less energy. There will be less energy violation. And because of this, this pair could live a little bit longer. We get closer to the black hole. By the way, this solid line here, this is the edge of the black hole. So when we get closer, the pair could live even longer. We get much closer, we get very close to the black hole, the pair could live longer and long enough for one member of the pair to fall into the black hole, never to reemerge again. Its partner will have nothing to annihilate against, and it is going to leave the black hole. And this is apparently the Hawking radiation. This is the common cartoon explanation for Hawking radiation. We have a pair creation near a black hole. One member of the pair falls inside, the other one has nothing to annihilate against, and it escapes. Now, the one that escapes obviously has positive energy. In order to have energy conservation, what fell inside must have negative energy. But as we're going to see in a minute, a particle outside a black hole cannot possibly have negative energy. Any particle outside the black hole always has positive energy. So what fell inside also has positive energy, and we don't have any energy conservation. We are going to address this in a minute. I just want to go into another picture of Hawking radiation. This picture that I took from a set of lectures by Jacobson. This is a set of lectures that he gave in Holland, I believe at the University of Utrecht. And this picture is the following. You create a pair. One of them is just outside the black hole, one of them just inside the black hole. Now, a justification for this picture is the following. In the common explanation for the Hawking radiation, both particles, the particle and antiparticle, are created at the exact same point in space. Well, the exact same point is not is something that has a good geometrical definition. I wouldn't say that it has a good physical definition, because we do not have infinitesimal distances in physics. The smallest distance that we have in physics is the Planck length. So there is some distance between the point where this one was created and that one was created. It may be one Planck length or it can be several Planck lengths. And if it is several Planck lengths, then one may be just outside and one just inside. With this picture, the one just inside can very well have negative energy that would balance the positive energy of the one coming out. So with this picture, we do have energy conservation, and with this picture, it is very clear that the total mass of the black hole is going to shrink every time we see a real particle coming out, because it has a companion particle with negative energy that gets absorbed all the way to the singularity of the black hole. The black hole loses mass, and eventually it shrinks. The same, yeah, go ahead.
Okay. You say that the particles with positive energy escape.
Correct.
What is to prevent them from falling into the black hole? And the reason I ask this is because the average temperature of the universe is 2.3 Kelvin, and yet for a supermassive black hole, or even just a massive black hole, we're talking about microkelvin. So why is this not a
We're going to go into this, Michael, into the temperature of the black hole, but as to why it escapes, let me state up front that in most cases, when you have this phenomenon, one particle getting created outside with positive energy, one created inside with negative energy, both of them will fall into the black hole because of the gravitational attraction of the black hole. In only very rare cases would one of them manage to escape. If one of them, the one with positive energy, has been created with a momentum that points straight away from the black hole, and it is high enough, it will manage to escape. This will be true only for a tiny fraction of the pairs that are going to be created here. And because it is true only for a tiny fraction of the pairs, the temperature of the black hole is going to be very low. We are not going to see a whole lot of those coming out. And in a little while, we are going to see why in the case of a smaller black hole, the temperature is actually much higher. Now, we can take the same argument to the inside of the black hole. We saw percussion outside the black hole. We can also have percussion inside the black hole. My understanding is that quantum field theory would still tell us that we have percussion inside the black hole, except that inside the black hole, whatever it is that we create is going to fall towards the singularity. So we are going to have percussions inside the black hole. Both of them or both of them can have positive energy or negative energy, or one positive and one negative. If both of them have positive energy, it is very likely that they will annihilate each other before they reach the singularity. If one of them has positive energy, the other one has negative energy, and they balance each other exactly, so they do not violate energy conservation, they don't have to annihilate. They don't violate energy conservation. They can live a long life, and at least long enough to get them to the singularity. So inside the black hole, we can have a huge amount of pair creation where both members of the pair are real, not virtual particles. They are real because both of them are under mass shell, and we conserve energy. Energy is not being violated here. And therefore, they can be created in abundance. The only limit to what it is that we can create here, the only limit to what it is that we can create here comes from the Pauli principle. We cannot create two electrons at the same time, at the same spot, in the exact same state. But you can create a whole bunch of electrons in different states with different energies, different spins. We can create electrons and quarks and all kinds of other particles, and muons and taus and neutrinos and antineutrinos in abundance, as long as we don't violate the Pauli principle. So this is, again, so far a cartoonish picture of what it is that we're going to see a little bit more seriously in the rest of this session. And so far, the major point has been, number one, that information is not at the periphery of the black hole. It is not preserved outside. It is preserved inside. And we are going to see how information can leave the black hole using this picture. By the way, in this case of pair creation, those two particles are entangled, just like those two particles are entangled. If this is an electron, then this is a positron. The spin are the exact opposite of each other. Same thing here. If this is an electron, then this is a positron. Their spin are opposites. Those are two entangled particles. They're not created freely. Just in order to preserve all the charges, all the quantities that are conserved in quantum mechanics. So let's go to the next metric, because this is where black holes start.
I have one question. I'm back finally. My mic is back.
What?
What is the
modified version of the Schwarzschild metric, because we look only at radial motion, where theta and phi do not change. So we just consider radial motion towards the singularity in the black hole. This simplifies a little bit the expression that we have here for the metric. One problem with this metric is that this coefficient blows up when r, the distance from the singularity, is equal to the radius of the black hole, which is 2gm. G is Newton's gravitational constant. Capital M is the mass of the black hole. We assume here that c, the speed of light in vacuum, is equal to 1. And R is defined such a way that if you have a sphere centered at the center of the black hole, and it reaches the point, or the radial point defined by R, then it has the proper size for the area of the sphere. Is infinite when R is equal to 2gn, because then you have 1 minus 1 to the power minus 1. This is going to be infinite. in order to get rid of this infinity, which is strictly a consequence of the coordinates. This is not an inherent infinity, unlike the infinity that we have here. Here, when r is equal to 0, we have an infinity at the origin, and there's no way to get rid of this infinity. This is a true infinity. This infinity is origin dependent, sorry, is coordinate dependent, and we can get rid of it by moving to a different set of coordinates called the Eddington-Finkelstein coordinates, which are defined as follows. First, we define r star by this relation. This relates r star to r. Once we have defined r star, we define the Eddington-Finkelstein time v as being t plus r star. With amazingly simple algebraic manipulations. If you try, you will be amazed at how simple they actually are. We discovered that the metric in the case of Eddington-Finkelstein reduces to this expression right here, again, assuming only radial motion. So the theta and the phi are still kept equal to 0. If we look at the light cone, in the Eddington-Finkelstein coordinates, we see the following. Here on the horizontal axis, we have r. This is the same Schwarzschild r as we had before. On the vertical axis right now, we have v. Instead of t, we have the Eddington-Finkelstein time. And what we see when we put ds equal to 0, which defines the light cone, is that one solution for ds equal to 0 is dv equal to 0 because dv appears in both terms. So dv equal to 0 is one solution for ds equal to 0, and this puts the horizontal line of that you see here for the light cones. So wherever you are, if you have a beam of light, a photon, moving towards the center of the black hole, in this picture, it will always be along this line right here. What about a photon that you shoot away from the black hole? It will have a velocity moving towards the black hole with the velocity dr dv instead of dr dt, given by this expression. We get it straightforward from this expression when you put ds equal to 0. And what we see is that far away from the black hole, when r is equal to infinity, this is 0, and dr over dv is 1/2. So it is going to be 1/2 the speed of light, but it is 1/2 rather than 1 time the speed of light because of the change of coordinates. And as we move closer to the black hole, we see that this light cone starts to close. At the event horizon, this part of the light cone becomes vertical, meaning that you cannot move away from the black hole. At the event horizon, if you shoot a photon away from the black hole, you will see the photon stationary at the event horizon. It is not going anywhere. As you move inside the black hole, you see that the light cone closes. Even if you shoot a photon away from the black hole, it will still move towards the singularity, as you see right here, and it will move towards the singularity with ever increasing speed. The speed is going to approach infinity. As you can see from here, when r approaches 0, this approaches minus infinity, and we have the minus sign because we're moving towards shrinking values of r, towards the singularity. And this is something that you have to keep in mind, that inside the black hole, there's no such thing as being stationary. You cannot just say, okay, I'm inside the black hole, I'm not doing anything. No, inside the black hole, you're always moving towards the singularity, even if you're a photon trying to escape. And this is something that we have to keep in mind. when we go to our next picture, in a Schwarzschild field, the energy of a particle in flat Minkowski space is given by this expression here. It is the square root of the mass square plus the momentum square, again with c, the speed of light in vacuum, being equal to 1. So if we don't have any gravitational forces whatsoever, this is the expression for the energy of a particle. If we do have some gravitational force due to a mass capital M, which may or may not be a black hole, it may be a star, or it may be our own planet, then we have to take into account the negative attractive potential energy, gravitational energy. The gravitational energy is negative because it is attractive. It causes R to become smaller. So we have a test particle of mass small m. It is being attracted to an object of mass capital M, and this is the gravitational potential energy. So far, there is no assumption that we have a black hole, but we assume that the mass capital M is spherical. We're only dealing with spherical configurations here, and we further assume that the small m is much, much smaller than capital M, so it does not really have any material effect on the stress energy tensor or curvature or anything else. Now, as long as we are outside the Schwarzschild potential of capital M, the minimum energy of a particle is obtained when the velocity of the particle or when the momentum is equal to 0. So this is the expression for the minimum energy of a particle outside a black hole. And we see that as long as R is bigger than 2gm, so this here is less than 1, the minimum energy of a particle is always positive. So if we draw here the minimum energy of a particle as function of distance from the center of the black hole or from the center of the mass capital M, we see that E at infinity, when R is infinite, this is 0, and E is simply the rest mass. So if we are talking about an electron at infinity, the minimum energy is going to be the rest mass of the electron. This is the energy of an electron instantaneously at rest, far away from the mass capital M. The energy for an electron instantaneously at rest closer to the Schwarzschild radius is becoming smaller and smaller. When you reach the Schwarzschild radius, namely when R is equal to 2gm, we have 1 minus 1 equals 0. So at the event horizon, the minimum energy of a particle is 0. What this means, one way to look at it is the following. If you have an electron at this point, right at the event horizon, and you try to get out, and you use all the energy that the electron has in your effort to get out, all the energy meaning you convert its rest mass to kinetic energy trying to get out, all you will be able to do is to stay where you are. You will not be able to get out. So this is another way of almost defining the event horizon itself. Now, in a very pedestrian way, and let me emphasize that this is a very pedestrian way for looking at the energy when R is less than 2gm. When we are inside the event horizon, then the minimum energy is what we saw before, but now we take into account the gravitational energy. Sorry, it's what we saw before, but now we take into account the fact that the velocity of the particle cannot be zero. There's no such thing as a particle instantaneously at rest inside the black hole. We just saw this a minute ago in the previous picture in the Eddington-Finkelstein coordinates. We saw that every particle inside the black hole is moving towards the singularity. The closer you are to the singularity, the faster you move towards the singularity. So the minimum velocity cannot be zero. If very naively we just plug in for the minimum velocity, the expression that we had before, we take the square, it is right here, then we have this expression for the minimum energy of a particle inside a black hole, and altogether we end up with this picture, where the minimum energy of a particle inside the black hole can be negative. By the way, if we ignore the fact that the minimum velocity of a particle inside the black hole has some finite value, if we simply ignore it, if we just take this expression as the minimum energy of a particle, we see that for r going to zero, the minimum energy is going to minus infinity. This is shown by this curve here, continuing with the dashed line, going to minus infinity. This contribution right here is going to counterbalance most of the negative energy that we would have here. And we end up with this expression for the minimum energy of a particle. And this is something very interesting. This is going to be the basis of all our discussion. The fact that inside the black hole, you can have negative energies. For instance, you can have zero energy. So if I'm at this point inside the black hole, I can create an electron-positron pair, both the electron and the positron with zero energy. I haven't violated anything. At least I've not violated energy conservation. I've not violated charge conservation. Their spins are opposite. So I can create an electron-positron pair, each one with zero energy. So both of them, both the electron and the positron, are real particles, not virtual particles. Both of them are on the mass shell, and both of them hurrying up towards the singularity. I can do even more. I can create one particle with negative energy, and then I'm going to create its partner with positive energy. So we see that at this point, we have lots of options here. We can create a particle with this kind of negative energy, or this kind, or this kind, or this kind, or this kind of negative energy. And in every case, we are going to create a corresponding particle with positive energy. So we have full energy conservation. We can go even further. I can create one particle here with big negative energy and a whole bunch of particles with a little positive energy. This is also allowed. I do not have to balance one particle here against one particle there. The total energy that I'm creating at this point has to be zero. This is the only constraint. I can create several particles with negative energy. I can create here an electron with big negative energy. I can create an anti-muon with big negative energy. I can create a neutrino with negative energy. And to balance all of those, I'm going to create a whole bunch of particles with positive energy, or maybe just one particle with very high positive energy, as long as all the conserved quantum numbers add up to zero. So as long as the total charge is zero, the total spin is zero, the total angular momentum is zero, total baryon number, total lepton number, hypercharge, and so on, add up to zero. So what we see here, the picture that we see here of the inside of the black hole is dramatically different from what we have in classical GR. Classical GR meaning without quantum mechanics, without quantum field theory. In classical GR, inside the black hole, everything falls towards the singularity. So inside the black hole, you're guaranteed to have absolute vacuum as long as you don't throw things into the black hole. If nothing is falling into the black hole, everything that has ever been inside the black hole has collapsed very quickly towards the singularity, and you have absolute vacuum in here. What you see outside. Outside, you see the Hawking radiation. Inside, you see the same effect as the Hawking radiation, but with all the radiations being created falling towards the singularity. And outside the black hole, this effect is very weak. Inside the black hole, this effect becomes very, very strong. It becomes so strong that what you end up with at every point inside the black hole is the maximum density of matter and radiation that is theoretically possible. Because you cannot create any more particles than in this scenario that we've just discussed without violating the Pauli principle. The only limit here was the Pauli principle. Now, let me be a little bit more careful about this statement. Let's go to this point, for instance. At this point, inside the black hole, at one instant in time, we can do nothing. If we don't do anything, we have not violated anything. Doing nothing does not violate any law of nature. Or we can create an electron-positron, each one of them with zero energy. That's another possibility. Or we can create an electron-positron, one with negative energy and one with positive energy. Or we can create another electron-positron pair with the same energies, but with opposite spins. Or we can create this electron-positron pair, and in addition, also a quark-antiquark, and maybe a muon anti-muon, and maybe a whole bunch of quarks antiquarks. So the actual state at this point is a superposition of a huge number of possible states, all the possible combinations that we can create at this point. It is a very large number, but it is a finite number. It is a finite number because there is a finite number of particles we can play with, and we have the Pauli principle. So at every point in space, at every instant in time, the wave function is going to be a linear superposition of a huge number of eigenstates, where each eigenstate can consist of any number of particles and antiparticles. By the way, so far I've been talking only about fermions. What about bosons?
Would you please repeat that? I'm sorry, please repeat that. I couldn't hear you.
Yeah, so far we've been talking just about fermions. What about bosons? What about photons? What about pi mesons, rho mesons, gluons? One way to look at mesons is bosons is the following. The archetypical boson, as far as Bose-Einstein condensation goes, is helium-4. Well, helium-4 actually consists of 6 fermions. So this specific boson is actually 6 fermions. We can look at a photon as being an electron-positron pair. At least according to quantum field theory, each photon spends at least some of its time as an electron-positron pair. And the same thing for gluon. A gluon can be seen as being a bound state of a quark and antiquark. A pi meson is a bound state of quark and antiquark. If you believe in supersymmetry, each boson has a fermionic partner. A photon has a fermion partner, which is we call photino. And in this case, you can claim that a photon is a bound state of a photino and a gauge fermion. Just as in quantum electrodynamics, we have gauge bosons, namely photons. In quantum chromodynamics, we have gauge bosons, namely the gluons. In supersymmetry, instead of having gauge bosons, we have gauge fermions. And in the case of supersymmetry, you can say that a photon is a bound state of a photino. A photino would be the supersymmetric partner of a photon, and the photino is a fermion, and it will be bound together with a gauge fermion. So if you believe in supersymmetry, and I don't claim that this is the winning theory right now, but this will also tell you that each boson is a bound state of fermions. So we can see all bosons as bound states of fermions, just like we look at the helium-4 atom as a boson, which is a bound state of 6 fermions. And we are back to treating fermions where we have to obey the Pauli exclusion principle. Now, so far, what I've been talking about, and I did not even bother to mention it, is the simplest possible black hole. By simplest possible, I refer to its pedigree. It is a black hole that has resulted from the collapse of a shell of dust and nothing else. So once upon a time, we had a giant shell of dust and nothing else, and the spherical shell of dust has collapsed into a black hole. Whatever I've been describing so far refers specifically to this specific black hole. I think it's time to look at something more relevant. The outermost circle is a giant shell of dust that is collapsing. The solid black circle is the event horizon, the Schwarzschild radius corresponding to this shell of dust. When this shell of dust has collapsed into this solid black circle, we have a black hole. So far, at this point, there's no black hole. Now, inside this shell, and again, so far there's nothing happening, we have one single electron. So what you're going to consider right now is the very simple black hole created by a shell of dust that is collapsing, plus one single electron well inside the Schwarzschild radius of this shell of dust. Once the shell of dust has collapsed into its Schwarzschild radius, we have a black hole. As far as this electron, nothing has happened. The electron is still inside the shell, and inside the shell, we have a flat Minkowski space. There's no gravitational attraction whatsoever because of the spherical symmetry. Now, once the shell has reached any point, like this point, for instance, inside its Schwarzschild radius, we are going to see the same scenario that we saw a minute ago, where gazillions of particles get created with total energy equal to 0. So once the shell has reached this point, we have fireworks. We have an explosion of particles of all kinds with total energy equal to 0. Let's look more carefully at what happens at this point where the electron is located. Same thing, when the shell of dust has reached this electron, it is going to create an explosion of particles and antiparticles, except that it is not going to create anything that contains an electron in the same state as this electron because of the Pauli principle. So what we see here is going to be different from what we see here, simply because we cannot violate the Pauli principle. How different it's going to be, this is not very important. What is important is that it is going to be different. Now, what happens 1 instant later? 1 instant later, because this electron just got a kick to move towards the center, it is going to move away. Meanwhile, we have all the other particles and antiparticles that have been created here. So during the next instant, the only thing that can be created here are states that have not been created before, namely states that include this kind of electron. So only those combinations that have not been created before are being created now. At the next instant, we are going to have something very similar to the very first instance. We are going to create all possible combinations except the combinations that include the state of this electron. So what we see, and so far it is very naively, very simplistically, is that the state of this electron is being preserved at this point inside the black hole, not the electron itself. The electron itself immediately starts moving towards the singularity, and very quickly this electron will be absorbed in the singularity. While this electron moves away towards the singularity, the information about the state of this electron remains preserved at this point inside the black hole. This is very similar to the picture that we saw before about an observer looking at, from the outside at a mouse inside the collapsing shell. If you have an observer right here, and let's assume that this is an object that can emit light. Let's, instead of just a simple electron, let's have some light-emitting object here. What you see from the outside is this object, but redshifted. It becomes ever more redshifted, but it doesn't move. It stays here at this location. This is what you see from the outside. And now we have an argument why this information does remain frozen at this point. Now, the way the information remains frozen at this point has to be taken a little bit more carefully. We saw that the information remains frozen at this point, but the electron falls towards the singularity. As the electron travels towards the singularity, at every point along the trajectory, it is going to prevent the creation of particles in the same state as it has. So the information about this electron is not going to be confined just to this point. It is going to be dispersed throughout this whole trajectory. It is going to be scrambled. Furthermore, there will be other particles falling from here into this position. And as those particles reach this position, they will affect what can get created here. So what is going to be created here is not the simple picture that we saw a second ago, where very clearly we have the information about this electron being instantiated here, and then it's complementary, and then again, this electron, then again it's complementary. It is going to be a much more complicated picture. But while the picture is becoming a lot more complicated, it is going to be determined by the fact that we had this electron here. If we had not had this electron here to begin with, the wave function that we see anywhere inside the black hole would be different. One moment, the situation that I described right now has a name. It is called unitarity. This is exactly what unitarity tells us, and this tells us about the preservation of information. Now, the information gets scrambled. It gets scrambled very efficiently, very quickly. It gets scrambled instantaneously. It gets scrambled to a point very quickly where it would be very difficult to reconstruct it. Maybe it will be even effectively, practically impossible to reconstruct it, but it never disappears, because the situation that we have inside the black hole is affected by the fact that this electron was here before. If we did not have this electron here before, or if the electron had a different state, if the electron had a different spin, for instance, what we see inside the black hole would be different. Again, this is just unitarity. And what we have here is a simple application of quantum field theory in a Schwarzschild metric, but all those particle creations are the result of quantum field theory. Yes, Mike, is a very dense object. We have maximum density that is allowed theoretically. You cannot even theoretically have any higher density than this black hole. So the information is preserved in a very physical object. It is preserved in an object that has the highest possible density. It is more than just writing information on a piece of paper. Writing information in a black hole, you have the densest possible substrate on which you write your information. Now, this substrate is obviously very dynamic. Everything in the substrate is moving towards the singularity. So you can say, this is not something very solid on which to which I can entrust any information. But the total state of the black hole does not change in time. At any point in time, you look at any point in the black hole, and it didn't really change. It always has maximum density. It has maximum density now. It had maximum density a second ago. It will have maximum density 1 million years from now. So while on the one hand, the situation in the black hole is very dynamic, it is a very stationary picture. It is a stationary picture, and it is in this stationary black hole, in this maximum density mass configuration, that the information is preserved. And this is the whole point here. It is exactly because of the Landauer principle that this picture has relevance, because we want to make sure that every bit of information is stored somewhere in space, and it has a physical instantiation. Here, the physical instantiation, initially it was at this point. We saw that very quickly it gets dispersed, it gets scrambled, it gets dispersed. So very quickly, we cannot say that it is stored at just this point. It is dispersed throughout the black hole. Actually, the information about this electron will be only within this area. It will not move away from this very narrow area, but it will be inside the black hole, and it will have a very physical instantiation.
Well, you see,
It depends on the fact that you have this high density of particles inside the black hole. It's not the minimum energy of a particle outside a black hole that we saw just a few minutes ago. We're outside the black hole, R is bigger than the Schwarzschild radius, and this is the minimum energy that a particle can have. I'm interested right now in the slope of this curve. The slope of this curve is given by the partial derivative of the minimum energy with respect to the radius at the black hole. Very simple to take care, the derivative of this expression. And when we take it at the point the derivative is going to be 2gm over r squared. When r is equal to 2gm, we are going to simplify 2gm at the top and bottom, and we are going to have this expression right here. We see that the slope of this curve, the slope of this curve is inversely proportional to capital M. So if capital M is the mass of the black hole, then we have this slope right here. Now, this slope, as you go a little bit inside the black hole, is telling you what is the minimum energy of a particle just inside the black hole, very, very close to the boundary, but just inside. And this is going to tell you what kind of energy budget do you have. You can create a particle with this much negative energy, but you cannot create one particle with even more negative energy. Now, this is relevant because, as we saw a while ago, the way we are going to explain Hawking radiation in this session is that it is due to the creation of one particle with positive energy just outside the black hole, compensated by the creation of one particle with negative energy just inside the black hole. Now, the more energy we have just inside, and by the way, those two particles, the one created outside and the one created inside, must be very close to each other, because typically the 2-point correlation function falls very quickly as the distance between the 2 points increases. If we want to have some correlation between this point and that point, it is going to be very, very weak correlation. The closer 2 points are, the higher the correlation between them. So we may be able to create one particle with negative energy here and one particle with positive energy here, provided both of them are very, very close to the event horizon. If one of them is any further away from the event horizon, this kind of pair creation is going to be very iffy and more likely completely impossible. So we are going to create a positive particle with positive energy right outside the event horizon. And the question is, how much of an energy budget do we have for creating this particle with positive energy? This depends on the slope of this curve. The deeper the slope, the more of an energy budget we have. So the temperature of the radiation that comes out, temperature is basically the energy up to the Boltzmann constant. So the temperature that you are going to see coming out of the black hole is going to be the energy of the particles coming out of the black hole. And the energy of the particles that are coming out of the black hole is going to be proportional to how deep this slope is. This is the energy budget that we have, and this is inversely proportional to capital M. So we see that the temperature of the radiation coming out of the black hole is going to be proportional to 1 over the mass of the black hole, which is what we have for the Bekenstein-Hawking radiation. Again, with the caveat that so far we did not come up with the proportionality constant. All the argument shows is that the temperature is inversely proportional to the mass of the black hole, but it doesn't give you the proportionality constant. It also mentions that the proportionality constant involves the Boltzmann constant, because this is the relation between temperature and energy. But we did not even try to recover any of the other details. If we create one particle with positive energy right outside and a companion particle just inside the black hole, with negative energy, the two are going to be entangled. If this is an electron, this must be a positron. If this has spin up, this must have spin down. If this is a muon, then this has to be an anti-muon, and so on. So that all the conserved quantum numbers are going to balance out to 0. So if we observe this particle coming out of the black hole, then we know the nature of the particle that was created inside the black hole. If we know that it was created inside the black hole, and presumably we can even determine when and where it was created inside the black hole, then we know that there was a place for it to be created at this instant, at this location, without violating the Pauli principle. Then we know that at that instant, at this point inside the black hole, there was no other, let's say, no other muon in this exact state. If what came out here is an anti-muon, then we know that here we have created a muon, and we know that there was not another muon in the exact same state at this very instant. So we get some information coming out about what is happening inside the black hole. And this is the way information inside the black hole gets transduced into the outgoing radiation. So by observing the outgoing radiation, in principle, if we collect every single quantum of radiation coming out of the black hole from its creation until its eventual evaporation, we should be able to reconstruct all the information that fell inside. Doing it may require more computational power that may exist in the universe, but this is just an engineering question that need not to bother us. But at least here we have an explanation for how information gets transduced from the inside of the black hole to the outside. A very strong caveat about it. I presented this picture to Juan Maldacena, and he did not agree with it. He claimed that this violates causality. And I cannot argue him on this point. It is true that I cannot have any information embedded in this particle right here related to information about the particle inside. Now, several comments about this. Number one, there's been one proposal for preservation of information inside black hole that explicitly violates causality, microcausality violation. This is something that we have discussed in this forum a few months ago. One problem with microcausality violation is that the way it is put together. In principle, you could have the paradox where I can ask someone in the past to kill my grandmother before my mother was born, leading to an obvious paradox. In this case, however, we do not even have microcausality violation. We do not have any possibility of information going from the present to the past. What we have here is something analogous to what we have with usual entanglement. When we have two entangled particles, let's say two electrons in the singlet state, and the two electrons are light years apart, as soon as we measure the spin of one electron, the spin of the other electron flips from being in a superposition state of up and down to being in a pure state. This happens instantaneously. Even though it happens instantaneously, so much faster than the speed of light. They can be millions of light years apart, yet this change takes place instantaneously. It does not go from the present into the past. So there's no violation of causality. There's violation of the speed of light limit, but no violation of causality. And this is something similar to what we have here. We may have a micro violation of the speed of light, very similar to what happens in entanglement. And we have come to live with entanglement. We know that entanglement is real. Entanglement has been measured. The collapse of the wave function due to the measuring one electron way far away, we know that it has an immediate effect on the state of its companion, which may be a good distance away. So this is the kind of entanglement that you are considering here. And this is the kind of correlation that you are considering here. It is no weirder than the entanglement of two electrons in the singlet state or two photons that are entangled in Alan Spector's experiments. It is the same situation. Yes? We are going to start at the very top. I have the minimum energy of a charged particle. The charge of the particle is small q, and we assume here that the black hole has an electrical charge, capital Q. The minimum charge of a particle with charge small q is equal to the energy that it would have if the black hole had zero charge. Plus, we have to add the electrostatic energy. The electrostatic energy is simply of a charged particle when you have an electron with charge capital Q, and this is going to be equal to its energy if the electron did not have any charge, plus the electrostatic energy. Just as a sanity check, if those two charges are opposite, one positive, one negative, then this quantity is negative, which is exactly what we need for attraction. So the closer we are to the center, the more negative this potential energy is going to be, which is very similar to what we had before without considering charges. If we just look at the gravitational energy, both particles have the same charge, then the product is positive. This term is positive, which means that we have repulsion. Now, if we look at the energy diagram that we saw before we had this picture, whoops. Before we had this picture for the minimum energy of a particle, this would be the minimum energy of an uncharged particle. If the product of Q times small q is 0 at the energy, so this is what we have. If either charge is 0, we have the black line. Now, if the product of the two charges is positive, namely if both of them are positive or both of them are negative, then we see that the energy is going to be higher. This is denoted here very qualitatively by the green line. We have a higher energy than the black line that we had before. If the product of the two charges is negative, one is positive, one is negative, then the contribution of this term is going to be negative, and the energy is going to be something somewhere along this orange line, which is below the black line. Again, very qualitatively. And what we see is the following. if we want to create a particle just outside the black hole horizon, as we've seen a minute ago, we have to create its partner inside. Now, let's say that capital Q is positive, and we want to create outside a particle with a negative charge, let's say an electron. In this case, what you will have to do is to create a positron inside. In this case, this product is going to be positive, and we are going to have less of an energy budget than we had when we had no charge. Similarly, if we are going to create outside a particle with the same charge as the black hole, so suppose that the black hole has a positive charge, and we are creating a positron here, then inside we are going to create an electron. Positive times negative is negative. We are going to have this line for the minimum energy that we can have inside the black hole, and we are going to have more of an energy budget for creating radiation. So what we see here is that if we have a charged black hole, it does not affect at all the temperature of zero charge radiation. We are going to have particles with zero charge coming out of the black hole with the same temperature as before. We're also going to have a radiation of particle with the same charge as the black hole, namely here. But those particles are going to have higher temperature. We are going to have more particles with the same charge as the black hole as particles with zero charge. If the particles have the opposite charge of the black hole, this is going to be this case, where the particle inside has the same charge of the black hole. There is less of an energy budget, and therefore the temperature of particles coming out with a charge opposite to the charge of the black hole is going to be less. So the black hole is going to be very stingy in radiating away particles with the opposite charges that it has. It is going to be very generous in radiating away particles with the same charge that it has. So every time it radiates away a particle with the same charge that it has, a particle with the opposite charge falls in and helps to neutralize the charge inside the black hole. So the black hole is going to lose its charge very, very efficiently. Now, let me be even more precise about what I mean by very efficiently. The black hole radius is a 2 gm. If the black hole is a skinny black hole, if m is small, this point is moving closer to the singularity. And what we see in this case is that this slope gets steeper and steeper. We just saw this a minute ago, that this slope is the inverse of this mass. So the smaller the mass, the steeper the slope. The steeper the slope, the more pronounced the effect of those changes is going to be. Therefore, the smaller the black hole, the lighter the black hole, the more ferociously the black hole will try to get rid of its excess charge. It will try to neutralize its charge. And very quickly, the black hole will become electrically neutral. And this solves the question of what happens to the charge when the black hole evaporates and collapses. As it evaporates, eventually it becomes very, very small. And then you can ask the question, well, what about all the charge that got trapped inside? The charge that got trapped inside never gets outside, but what is happening is that opposite charges keep falling in. If the charge inside is positive, the negative charges keep falling in, neutralizing the positive charge inside. The smaller the black hole, the faster this mechanism. Following. I mentioned that at every point inside the black hole, a huge number of particle-antiparticle pairs get created, and they all move towards the singularity. They all move in the same direction, so they all have momentum in the same direction. It looks like we do not have conservation of momentum here. It looks like a violent violation of conservation of momentum. This is something that can be solved, and I was hoping to do it today. If not today, then maybe some other time. And another issue that is popping up here that we have not addressed at all is the following. Schwarzschild metric has been derived for the vacuum, and it is valid only in the vacuum. We have a spherical distribution of mass. It can be a very tight distribution. It can be a very broad distribution. It doesn't matter as long as it is spherical. And the metric itself is going to be valid outside this mass distribution. Very explicitly, in order to derive the Schwarzschild metric, you use Einstein's equation, where the Einstein tensor is proportional to the stress energy tensor, which is 0 in vacuum, and therefore the Ricci tensor has to be 0. And this is what gives you, when you do some algebra, this is what gives you the Schwarzschild answer. We just saw that if you take quantum mechanics into account, or if you take rather quantum field theory into account, then the inside of the black hole is far from being vacuum. It is extremely dense. Then you can ask yourself the question, if we are not in vacuum, is the Schwarzschild metric at all, does it still have any validity whatsoever? What is the energy momentum tensor inside a black hole? If we have this kind of energy momentum tensor, what is the solution to Einstein's equation? Now, Karl Schwarzschild has been very kind to provide us with two solutions. One solution in vacuum. This is the solution that we are all familiar with. He has also provided a solution inside an incompressible fluid. And this would be the case, for instance, for planet Earth. If you want to go into some spot inside the planet, then you're going to use the Schwarzschild solution for incompressible fluid. This is a very well-behaved solution. It tells you that at the center of the Earth, you have a flat metric because you're not pulled in one direction more than in any other direction. You have basically zero gravity at the center of the Earth. But what we have here in a black hole is very different from incompressible fluid. Incompressible fluid means that nothing moves. The picture that we saw for the inside of the black hole is very dynamic. So we may be faced with the situation where neither one of the Schwarzschild solutions could be considered as being applicable. This is something that has to be addressed.